welcome everybody to today's webinar. My name is Dan Combest, and today's final Learn by Example webinar, I'll be talking about simulation studies with Python and elements. During this session, I have several key goals. First, I'd like to introduce some key features about Python and elements integration, and hopefully by the end, you'll obtain a sense of how to record these Python journals and use them within elements. I'd like to accomplish this in around 20 minutes, maybe a little bit less, maybe a little bit longer, and we'll answer all the questions via email post-webinar. So for the webinar invite, if you just hit reply, it'll go directly to me. So far, we've covered lots of different topics in the Learn by Example series. We covered an introduction to vehicle aerodynamics with elements. Then we talked about vehicle tire modeling with elements. Then I did a topic on customizing elements templates. And then my colleague gave a very nice discussion on aerothermal simulation. So all of these you can find on various channels. You can find all the videos on our YouTube channel if you missed them. And you can also find past webinars and the current Learn by Example series for both Helix and Elements on our YouTube channel. If you'd like to read more, you can check out blog.engys.com for all the recordings and other articles related to our software. For questions, again, you can reply to the email invitation for the webinar, or you can send an email directly to info@engys.com. Today I'll cover several key areas. The first one is workflow automation. Then I'll talk about elements and automation. Then I'll do a little bit of Learn by Example and leave you with a few take-home messages. First of all, CFD simulation is complex. There are many different steps from geometry preparation, mesh generation, case setup, simulation, visualizing the data, evaluating the data, and then how do we use all of this within our CFD analysis toolchain. Oftentimes, companies develop best practices to leverage methods that are known to provide results needed for design feedback. So we like to develop these repeatable steps and know-how internally on teams for sequences that are known to correlate well with experiment, to give results that give good information back to design engineers. We also like to develop best practices to create consistent methods among team members. So one person on the team who may have 2 months of CFD experience may generate a different result than those on the team that have decades of simulation experience. And so best practices help normalize this, help unify our efforts on a team to maximize results, maximize compute time, maximize licenses that might be used. So best practices offer a lot. It also enables repeatable processes, and overall it decreases costs. If we do something that we know will work, it's a very short path to the result. And just a note, when I say experts, I mean an expert is someone that can do things consistently with high precision and high accuracy. And so developing a best practice can project this expert status onto other team members. It can really help them do things consistently and with high precision and accuracy. Repetitive tasks are really an opportunity to reduce costs, both time and money, apply expert knowledge. If we're doing things over and over again, we can share this between team members and share experience and really figure out the most efficient way to apply the best possible route or steps within these repetitive tasks. It allows you to seek support from other team members. So if you're doing things in a repeated process, if it's documented or if it's automated, you can pass this off to some less experienced teammates, or even outsource or insource this to other teams. Automation, repetitive tasks are an opportunity to automate and streamline, and really this is the core of what Elements does for automotive simulation, especially for aerodynamic simulation. We're able to boil down different meshing strategies, numerical settings, simulation strategies, what data to export and automate. And a lot of automation is already performed within the graphical user interface of Elements. Now remember, there is a necessity to balance the cost to build this automation platform and perform the automation versus performing by hand. So if you're automating a very small task, it doesn't make sense if it is extremely low cost. Let me talk a little bit more about Elements and automation in general. So first off, why Python? Why do we even care? Well, Python is great because it's easy to learn. It works across operating system, and it really possesses a rich library of mature and evolving tools. So Python is a really good language to use for automation within software because other users may already have the understanding of the syntax of Python. They may have already used this in graduate school or undergraduate to perform other types of simulation. It is really perfect for automating tests, and it's a common interface between other software, both open source and proprietary, from preprocessing and meshing to post-processing and rendering. So there's lots of opportunity for cross-collaboration between different software packages with the right team of engineers to set up the toolchain. In terms of Elements and automation, some of the key features. So the Python macro language is used to automate the execution of elements from the command line. Okay, so we'll build these scripts and then we'll execute these scripts from the command line. It allows the user to automatically build macro scripts with journaling. And so when I say journaling, I mean it's a methodology in which it records the different steps that users take while they're using the graphical user interface, and it writes out the Python script itself for each one of the actions that a user takes. Now, this is a really key process because, simply providing a Python API is fantastic. However, then the bottleneck, then the difficult part becomes, how do we build these Python scripts effectively? And if it takes much more time to go through trial and error or sift through API documentation to try to figure out how to link together and flow our different analysis steps inside of a single Python script, that's one thing. But by using journaling, we're able to lower the barriers to automation by recording exactly how a user works inside of the graphical user interface. This journaling process supports mesh creation, case setup, running, and also the view tab, which is the post-processing step within Elements and our other software Helix. All right, so let me jump over to the Learn by Example. Today I'm going to show you how to set up a recorded journal and then show you what the output is and just kind of point out some of the important features. This may be a very familiar case because this is the exact case that I used for the first Learn by Example webinar that I did a few months ago. For this case, we're going to use the automatic hex-dominant parallel meshing with best practices for stock car external aero. So in this case, I added maybe a few extra assembly types. This is going to be a transient incompressible flow analysis with DDES. So today I'm not going to actually execute or mesh, I'm just going to set up the case and show you the Python. Here there's a test velocity of 38.89 meters per second at 0 degrees yaw. I'm going to point out if we wanted to do a yaw study where we might want to actually adjust the yaw. For this particular case, it's an open road setup with moving ground and rotating wheels. And the wheels are going to use the standard wheel treatment inside of Elements. So if you saw the other Learn by Example series, which I use GRF, that's a special wheel treatment. For this, because there's no grooves on the tire, we're just going to use a rotating wall boundary condition. And for simplicity, because we're not going to actually care about the underhood thermal effects, we're going to ignore thermal, and this is going to be a cold flow experiment. So let me shift over to Elements. So when we start the client server setup and we go through the client server widget, we're able to select what kind of resources, whether this is an HPC resource or if this is a local resource. For now, I selected local resource. Now, what we want to do is journaling to capture every step that we're going to take along the way. So I'd like journaling to capture me creating a new case. So I've already started my client server. Let me just close that. And so right now, there's no case loaded, nothing created. So let's click Start Journaling. And for here, it's going to ask me to save the journal somewhere and give it some sort of name. So I'll call this yawstudy.py. And I'm on Windows, so I'm going to keep this on my desktop. And let me hit save. All right, so now it's going to be recording everything from all my interactions or everything that I do within the GUI, and it's going to record this inside of this script. So let me see if I can navigate this. Let's go to yawstudy.py. Let me double click, just so we can kind of see what's happening. All right, so there's the first step. I've started Elements and it's recorded that step. Now, here's the thing. It's not going to record every step inside of the Aero Wizard until I actually hit Apply Defaults. So before I do that, let me create a new case. So let's do New. And I can store this on my desktop, or I can create a new folder, and let's call this Yaw Study. Create. Let's go down to Yaw Study, and this is going to be my parent folder. And let's call this Yaw Angle underscore V1, just for fun. And for this, let's do 128 cores, and let's run this in parallel. Let's create. Now I'd like to leverage the Aero Wizard. I could, if I wanted to, go through and use the general CFD interface and go through the meshing, setup, solver, and view tab. I could set up everything manually, all the boundary conditions, all the mesh settings, everything like that. And then every one of those steps would be recorded. Now, what's actually very powerful inside of Elements is that I can use the Aero Wizard. So it combines all of the automation that already exists inside of the Aero Wizard and allows me to record a Python macro or a Python journal to capture everything inside of the Aero Wizard. So here is another template that I made dealing with motorcycles. Today I'm going to use the Open Road Elements defaults. Let me click the configuration. Let's go to body type. Let's click stock car. Let's go to vehicle geometry. Let's hit import. We go to NASCAR. Let's hit open. All right, so if you remember from the first webinar, this starts out as one single STL, so let me go through and pick out a few components and actually recategorize them. As a minimum, I need to have body and wheels. So I've got my wheels, and let me just categorize a few extra components here. External detail. So I don't necessarily want this detail on the hood of the vehicle. I could if I wanted to, but let's go to remove and remove that component. All right, let's go to interior, and let me use another assembly type called cockpit. Cockpit has very fine refinement, but it doesn't have layers. And then let's also go to window nets. I'm going to assign that as type cockpit as well. And then let me do underfloor, and let's assign that as underfloor. All right, so I've got several different types of components that are all categorized, and when I categorize these, it's going to have a different mesh treatment, so how much refinement, how much distance refinement, how many layers are on the surface. And for the wheels, it's going to try to sense the center of rotation of each one of these wheels. If it doesn't, then I'm able to set this and use different tools inside of elements to determine the center of rotation. If there's any toe or camber to the wheel, then I can also use these tools to determine the center of rotation and axis of rotation. It also does the task of determining where the wheels are with relation to each other in terms of front left, front right, rear left, rear right. And then it categorizes these different components. Now you'll notice that I have FL, FL, FL here. We can also prepend some of our STL surfaces to actually pre-categorize things when we bring them in. That's also a possibility. I've covered that in other webinars. All right, so we have the parts categorized. I'm confident that the rotational axis of each one of these wheels is correct. I'm happy. I need to move on to the next step. Let's go to the wind tunnel. And you'll notice right here that the floor is a little bit high, so let's have it sense the floor. Kind of keep this number in your mind, minus 0.7. Okay, great. Now, in this case, typically I do a 0-degree yaw, but I'd like to at least point out where I might want to adjust the yaw and turn my Python script into a function. One of the things I like to do is, if it's recording a journal and I need to be able to go and find that number very fast, or that entry very fast within the Python script, I'll enter something very, very memorable in terms of a number, and something that wouldn't be said anywhere else, and then I can easily go find that. So let me just enter pi for yaw angle, and then let's go to the run settings. Here's the wheelbase, and then I can either sense the frontal area. Let me go ahead and do that. Okay, so I've got the frontal area. Now all I need to do is hit apply settings, but before I do that, let me go back and let's look at the script, see whatever's changed. So far it's only changed the case name and then the number of cores. So let me jump back. Let's hit apply settings. And then let me hit save case just for good measure. All right, fantastic. Let's go back and look. Let's refresh. And now we see all of the different steps that we took. We didn't have a porous media, so we didn't have to set a porous media. It's gone through, created the case, created the number of cores, it's selected the template, it's selected the body type within the template, it's selected the STL files and imported them, and then it's started to assign the different components and subcomponents from the STL into different component types and body types. And so here we've got the different wheel geometry locations. Let's go down even further. We've got type interior to cockpit. So it's gone down, and here's where we deleted one of the subsurfaces. Here's where we've recategorized the interior as cockpit and the window nets as cockpit. The underbody and underbody pan, it's all called underfloor. So we've gone through and set these different components. Now, here's another one where we're updating the wind tunnel. And so you can see right here, here's 3.14159, so this is the yaw angle. So if we wanted to convert this whole script into a function, we might want to change this if we were going to do a yaw angle study. Here is the the reference area, and then here's also the wheelbase. Here's where we see applying the defaults, and then here's where we see saving the case at the very bottom. If we wanted to, we could, in theory, turn this whole set of steps into a function. If we wanted to do that, what we would do is we would highlight everything, go all the way down to the bottom, and then I would hit tab, and then we could come up here and we could define a function. Okay, so this whole set right here could be a Python function. If we wanted to, we could pass a variable here, and then we can actually develop a script after this and pass something to my function. Say if we're doing 2 degrees, something like that. We'd also need to go back within our function itself and maybe turn one of these entries, something like that, into a variable that we're going to adjust with our function itself. We could put this inside of for loops. We could call this from other scripts. We could do lots of different things. We can pass strings if we want to pass different surfaces, if we want to do some sort of design of experiments with different surfaces. So here in this even simple example, we're able to show importing different geometries, recategorizing them, setting up different test velocities. So if we were to do this by hand, this would be 5-10 times longer if we were to do it all in the general CFD interface. All right, so let me close that, and let's go back to the presentation. Now, running the script, we run the Python macro file. We can edit this. We can modify it using external editor. I was using Notepad++. You can use another one. We can execute the macro file from the command line. For Linux, we just need the full path to the elements.sh, and then we pass a -python execute, and then the full path to the .py. Within the Windows command line, we need to have the full path to the ENGYS.bat file, and then the same flag and path to the script.py. And that will execute the Python script itself. If you have a local license, then it will find the license on your machine. If you have a license server located somewhere else, then you will need to export some variables in order for the Python script to look for the license server location. That type of information is in the documentation for Elements. So, or you can just send an email to support and we can walk you through the whole process. Just a few take-home messages. Simulations can be tedious to manage and tricky to consistently set up. This means models, all the different mesh settings of refinements and layers, and also post-processing and all the information that we want to extract from a simulation. Automation enables a huge gain in efficiency for engineers. And I mean that engineers are able to turn around and use their efforts at other places. So rather than spending a lot of time setting up cases, worrying about whether they're set up correctly, automation allows the engineer to spend more time looking at the results and thinking about how to apply that to their designs. Elements is really a framework for automotive simulation, and it originally centered around aerodynamics, so further automation is an added benefit to those users. There are many automation topics that were not covered within this short 20-minute discussion. There's post-processing of pre-run cases, there's sensitivity studies of things like yaw angle, ride heights, turbulence models. We could also do a sensitivity study of meshing Or we could do a sensitivity study on averaging time or transient time steps, something like that. You can also do discrete design of experiments, swapping of geometry if you wanted to. So thank you everybody for coming today, and I look forward to answering everyone's questions.